So thank you very much. And as a former high school teacher, what I would like you to leave today with are some things that you can impart to your own students. So I have quite a few slides. I will not go through everything, but you will be able to access them afterwards for lesson plans and other things. And at the very end, with the thanks of my PhD student, we've put together a whole series of online links that you can use for videos, for photos, for lesson plans, etc. So with that, what I'd like to do is to start. And what we'll be talking about today are landslides or mass wasting. And I will first do an introduction. I'll talk about some of the processes involved, some of the factors influencing slope stability. Then I'll talk about triggered landslide events, the idea that one earthquake can trigger many thousands of landslides. From there, go into how landslides interact with road networks, hazard assessment of mass wasting, if time, and if not, it's in the slideshow, prevention and mitigation of mass wasting, and then the further resources. Now, I'd like to start out with asking you, I have 3 bottles here filled with sand. And I won't tell you why. We'll get into this a little bit later. But I'd like you to slowly rotate this as it comes around. And you'll see we'll be discussing it later. And this is going to be one of the very inexpensive demonstrations that you can do with your students. So if we could start one here. And can you put them somewhere in the back? Good. So just rotate it very slowly and look at the grains as they're going through. So let's start off with an introduction. First of all, what is mass wasting, or landslides if you want? They're the downslope movement of rock and regolith near the Earth's surface. And it's mainly due to the force of gravity. And we'll see later there are 2 major forces, gravity and water, that are going to control the landslides. The regolith is unconsolidated rock debris. This includes any soil horizons, it includes the overlying bedrock, and basically this downslope of material is what we call commonly as a landslide. Now, mass wasting is very important for erosional processes. This is what shapes a lot of the land around us. This erosion, it moves material from high to low. Its streams and glaciers can then pick up the material and move it out of the system. Sometimes it's very slow, but often it can be very, very sudden. So we have a gradation from very, very slow to very sudden, and we'll see that with the processes. As human populations expand, as we get more people living in places, mass wasting processes tend to intersect with human infrastructure, and this is why it is becoming such a problem. As an example, we have had many fatalities due to landslides, like many of the natural hazards that you've been seeing during the course of these couple of days. Just one earthquake triggered landslides. This was 12,000 to 20,000 fatalities in 1949. We've had more recent examples. The Wenchuan earthquake caused quite a few fatalities, and we have many, many other examples of triggers resulting in many landslides. In a typical year in the US, there's $1,000 million of damage and 25 to 50 deaths. In other countries, it can be much higher due to higher population densities, lack of zoning laws, lack of information about mass wasting, and lack of emergency preparedness. So the knowledge about these relationships and the local geology, they can lead to better planning. And one of the things you should take away from today is that many of the major disasters that we have had with mass wastings could have been foreseen. We as a society, we can't predict exactly where landslides will occur, but we know where has high susceptibility of landsliding. So we can do something about mass wasting and the cost. In this next part, I'm going to go through it quickly, show you some videos, some photos, and talk about just that there are many different kinds of mass wasting that exist, from very slow to very fast. There's lots of classifications in the landslide community. I'll cover it rapidly. There are photos and videos. These are excellent for high school classes. You can use these and base a couple of hours around them. Students can go off and do it on their own, or you can show them in front of them. See notes on each slide for links and details. Now, processes for landslides, they generally grade into one another, so the classification is often difficult. And geologists, we love to classify things into one thing and another thing and another thing. And this has been done a lot in the landslide community. Broadly, we can break them up into slope failures, and this is the sudden failure of the slope, and this results in the debris going downhill, and it bounces, and it goes down like this. The other type is sediment flows. You get liquid involved, and liquid can also include air, by the way. But water or air, they get involved and they cause things to flow down. So slope failures we can divide into slumps, falls, and slides. This is an example of a slump block here. Here's the surface of rupture. Here's a river down at the bottom. The sediment gets down to the river and it takes the sediment away. Here's an example in the real world. This is La Conchita in California from 1995. Here's the headscarp, the slump blocks. The next one I'm going to show you a video. All the details are here. This occurred in San Mateo County. This is another slump, and you can see the slump coming down over the course of 6 or 7 days. And this is quite a spectacular example of a slump. They knew it was going to happen. They could see signs beforehand, and so they started to monitor it. Rock and debris falls. This is literally gravity. Comes down, takes the rock. There's no fluid involved. And this is an example of a rock fall. This was in Fraser Canyon. It blocked the road for many, many days afterwards. Rock falls are very common. And I looked at the 17 countries that the high school teachers that you're all from. Landslides are a part of each one of your countries. It is an issue. So this is something that should be of immediate interest to the high school students that you're working with. Rockfall 1999, this was Sacred Falls. This was 8 deaths and many injuries. What happened is people decided to put their tents right near the cliff, forgetting to look at what was at the bottom. And the idea is there were rocks there. They put their tents there. Well, there was a whole bunch of rock falls, and many were killed during that period. So if you're going to pitch a tent, be careful where you pitch it. Don't put it right next to the cliff. The next one is a video. This is on the Salton River, Oregon. I'm just going to show part of this, and if you could click on it. And here we can see the rock fall coming down. These were actual kayakers that were involved. And we can see it's quite spectacular. Now look at what's going to happen. This is going to dam up the river. The river's going to dam, and this is often a secondary hazard from mass wasting is the rivers dam up and you end up with a flood. And there have been more fatalities from the damming of the rivers after a rock fall or other sorts of mass movement than other things. This is rock and debris slides where literally it goes along the bedding joints. Here's an example of a house at the very bottom. This was in Fluvio. These are houses here, and it literally slid down. This is one that I'll just show the first part of it. This is a very large one in Italy in 2010. And as I said, I'll just show part of it, but this whole side of the mountain, there were no injuries, no deaths, because they knew ahead of time that this was going to occur. They didn't quite realize how dramatic it would be because it ended up taking a huge, huge area here. Okay. The next type of classification are sediment flows, and this is where debris flows come down and it mixes with water or air, and this causes the material to basically flow down, and we'll talk a little bit later about the processes of how that accelerates things. So if we go into sediment flows, we have slurry flows where there's 20 to 40% of the flow itself is water. After 40%, you're essentially getting into a river. 0 to 20% are granular flows. And what you have with these little bottles right now is essentially granular flows. You're looking at how it's flowing down if you're looking at these. And we have many classifications. This is just one where we think of it as classified by the amount of water that is taking part with the sediment itself. So slurry flows 20 to 40%, granular flows 0 to 20%. I'll just show you some examples. This is a debris flow. It's coming out, it's coming along. This is in minutes, it's about an hour, it's concealed here, and it comes along. And the thing about these flows is they can go very far distances and they can go very quickly. So they can become very, very dangerous. And this is often where we have dramatic numbers of fatalities and injuries, is when we have a rapidly moving flow that hugs along the topography of a river basin and there's a town in the way and it hasn't been diverted. So this has happened in a number of countries. The most recent very serious one was in China about a year and a half ago, where there was, I think it was 10,000 fatalities in that, the Zhenchuan earthquake, the Zhenchuan disaster. And I visited there last year, the aftermath of that. This is an example of a debris flow in Venezuela in 1999, and you can see when the town gets in the way, there were many, many fatalities as a result of that. And you have big, big rocks that can be carried as part of this flow. The next one I won't show here. It's a slurry flow. It's good for high school students. Granular flows 0 to 20%. And we get into things like creep. Around us, soil is moving all the time if there is some sort of a gradient or slope. So if I have a hill, it is moving. Creep can be on the orders of millimeters over years, but it's still moving. And we can see evidence of this with trees. And one thing that I would enjoy to do if I had high school students, I do it with undergrads now, is to say, let's go out and look for evidence of creep in the environment outside. So we can see it in many, many places. So always this is moving very, very slow. This is a bit faster. It's an earth flow, literally coming out. Here's the lobe here, toe, scarp. Okay, so that's a very quick overview of some of the types of mass wasting. Let's look at the two major factors. And I've passed around, I don't know if everyone got it, a little bottle where you took some sediment. I'll come to that in a moment. So gravity is one thing. So we know that if I were to drop this right now, that it is going to fall. That is gravity coming down. That is one of the essential forces that is driving landslides. If something is on a flat surface, it's not going to move. It's stable. But it's very rare we have anything on a horizontal surface around us. So we can break this down into the perpendicular tangent and a perpendicular force of gravity and the tangential part. The tangential part, the gravity part is going to hold it in place. The tangential part is going to work against the force of friction. And as this gets steeper, the tangential part is going to overcome the perpendicular part and the rock will move here. So we talk about shear strength, and the shear strength is all the forces resisting movement down the slope. They include frictional resistance. They include the cohesion of the particles themselves. When the shear stress gets greater than the shear strength, the object's going to move. Shear strength is going to be increased by steeper slopes. So we know if we have a steeper slope, this is going to be one of our ways of doing hazard mitigation. We go around and we look at digital elevation models. And we look at where is steeper, where is less steep. So that's going to be our first way to look at where is more at risk. It's decreased by lowering the cohesion among the particles and lowering the frictional resistance. Water is very important. So water is not only directly involved in the transport of material, but it also plays an important role in how the particles themselves interact with one another. So imagine you have a sand castle. If we have a sand and we put too much water in it, the walls won't form. But if we have it just right, we can get nice walls. And if we have no sand, no water, it's really, really hard to get any sort of a wall forming. So you can do this with your students. We can talk about dry sand here. We look at the angle of repose, and what we have are grain-to-grain interaction of the particles themselves. But if we have wet sand here, the angle of repose, we have a surface tension here. And so we can then create that surface tension and create the wall. And then we have water-saturated sand. The water completely surrounds all the grains here. So we can do that with an inexpensive student demonstration. This was one of my PhD students a few years back. She's here at EGU now. And here we have dry sand. We rotate it, and you can also rotate it to watch the little landslides occurring. You then put in just a little bit of water, and you can see a wall forming here, and then you put in a lot of water, and it literally flows. And these are some of the major forces that we see happening with mass wasting. Another example of an experiment you can do with students is take water between, you can sometimes buy these off the web, and basically you have two pieces of glass plate with sand in them, and it's quite fun. I used to do this with a webcam for my undergraduates and show it to everyone and then pass it around. And then you get an idea of subaqueous landsliding. And these are some of the things that you can see underneath. There are a whole bunch of demonstrations. I had a fellowship at one point. It was just a few £1,000s to put together hands-on demonstrations because I enjoyed doing them. You can download this. There's both a talk and a poster. Some of these you saw yesterday. I stopped by for a little bit and I saw all of you playing with the different natural hazard demonstrations. But there are slinkies and tornado tubes and air pressure and other things in here. So these are all simple demonstrations that you can do with your students. Okay, coming back, let's move to triggered landslide events. The major triggers of landslides are basically earthquakes and rainfall. Now, mass wasting event can occur anytime the slope becomes unstable. Sometimes, as in creep, it's always unstable. It's always moving, a little bit at a time, but it's always there. Other times, triggers can occur that cause a sudden instability to occur. So the major examples of triggers are earthquakes, major shocks where we shake everything. And in the process of shaking everything, it basically decreases some of the cohesion between the particles. So we come back to the gravity, we come back to water. Heavy rainfall, sudden snowmelt, changes in hydrological condition. This reduces the grain-to-grain contact. It reduces the angle of repose, and you end up with landslides occurring. It also saturates the rock and the regolith, and it makes it much heavier. Volcanic eruptions, these are shock-like explosions, earthquakes, melting of stone, crater lakes empty. So these are examples of major triggers. And the major triggers here, the number of landslides that result after a trigger could be none, it could be one, but it can be tens of thousands of landslides that occur in the minutes to weeks after the trigger occurs. The areas of these landslides range from very small, generally meters squared, to kilometers squared, so over many, many orders of magnitude. We have very few big ones, more medium ones, lots and lots of very small ones, and very, very few very, very small ones. And that's something the geomorphology community is still working on. Why do we have very, very few very small landslides? Other triggers of landslides, those were the major ones: earthquake, heavy rainfall, volcanic eruption. Other triggers include slope modification. This can be by humans. So we can go to a road, do a road cut. By doing a road cut, we're changing the angle of repose. By changing that angle of repose, we're causing an unstable situation where a slide will often result. Undercutting in a river, same thing. We're changing it so we get a slide slump, and fire can cause the removal of vegetation, and this results in the regolith becoming less fixed over time. You can add mass to a region. So if you build something on top of a region, or you put mining waste, or you put some sort of other waste, or some sort of water leakage, this causes it to be very heavy, and this can trigger a landslide. Now, I'm going to show you a couple of examples of triggered landslide events. So this is now getting into some of my own research where with Fausto Guzzetti, Paolo Reichenbach, and Don Turcotte, we did research looking at 3 major triggered events that occurred. And these are the second 2 here is data that you can actually download off the internet. If you're interested, email me. My email is in here. I will send you papers or whatever and get you started on that. But I'm going to talk about 3 inventories very quickly. The first one in more detail from Umbria in central Italy. This was the result of rapid snowmelt because there was a sudden change in temperature. It basically, in a day, the temperature rose quite a bit. It caused a whole bunch of snow to melt. This caused a hydrologic regime change where many landslides were triggered. The next one is Northridge, California. This was an earthquake in 1994. It shook things, had over 10,000 landslides result. The third one is a hurricane, which in the sidewalls of the hurricane was rainfall, because often in hurricanes, in the sidewalls of them, you get a lot of rain in those sidewalls. So we're getting back to our major triggers, earthquakes, and changes in hydrologic regime. So let's look at the first one from Italy. Here are some examples of some of the landslides that occurred in Umbria region in Italy. This is a house for scale. Here you see a landslide. And here you see the road has been damaged, a smaller one. Here's a bigger one with the road for scale. And here's a very, very big one with there's some houses in the background. And they come in all sizes. Again, very few big ones, more medium ones, and we'll see some of the statistics of these in a moment. Now, when we have landslide events, often what will happen for major events is the landslide experts will go out and they will map all of the landslides that occurred. This is a very time-consumptive process. Each one of these represents landslides that occurred as a result of the rapid snowmelt in January 1997. So here we have Italy. This is the Umbria region of Italy. Each one of these dots represents landslides, 4,200 of them. And this is an example of some of the detailed mapping. Now the detailed mapping here, originally what we would do is we'd use air photos. And if you imagine taking 2 fingers like this, crossing your eyes, and you can see a little finger in the center, this is what a stereoscope is doing. And you're taking 2 pictures that have been taken at slightly different angles. You're merging them together so you see a 3D image of them. And this is an example of some of the scientists at CNR working on the air photos. This is a dual, so they can outline very carefully each of the landslides that occurred on tracing paper and then later transfer that to a map. So that is how we used to do it. We still do it quite a bit that way. Now we are using more remote sensing sorts of tools and remote sensing images at high resolution. And this is an example of a scientist working with remote sensing images, doing it in 3 dimensions. So it can take literally human years to put together these maps. So that is one of the efforts that we do. Why are we interested in these maps? It's because knowing where landslides have occurred give us an idea of the probability of landslides occurring in the future. So what has occurred in the past for many different natural hazards is helping us for the future to know where is a region more susceptible or less susceptible. So if we look at Northridge, there were 11,000 landslides here. This is an example of one of the big ones that occurred after the earthquake. And now anytime there's a big earthquake or a big hydrologic event, I look in the literature to see, have there been also a lot of landslides? We expect it to happen. It is one of the forecasters of some sort of mass movement activity going to happen. So the more I know about the relative regime of earthquakes, the more it will tell me about the possibility of landslides in the future. This is the hurricane in Guatemala, Hurricane Mitch, in the very, very big hurricane. Many, many hundreds of kilometers across. This affected several countries, actually. The United States Geological Survey, this is an open file report, which means it's accessible online, went in and they mapped all of these landslides after they occurred. So to map the landslides, you need pictures before and you need pictures after the event occurred. And you basically look at the difference between the topography. And then you go out in the field to double check what you have done by hand. All right, frequency size statistics I'll mention very briefly. And this is basically the idea, and this is the part of research I do a lot of, is I look at the statistics of natural hazards. And I look at wildfires and landslides and earthquakes and floods. I'm doing a talk in a couple days on tornadoes and the frequency size statistics of tornadoes. When I looked in the EGU program for tornado, I found there was only one talk amongst our 14,000 abstracts on tornadoes. So obviously this is not as of interest, but I find it quite exciting. And the idea is to say how many very big ones, how many large, how many medium, how many small, how many very small. Because if we have an idea of the statistics, then we can give some idea to civil protection agencies what to expect for the future. So here, this is part of work where we took these three inventories, we looked at it, this is on a log scale, linear scale, and it's very different from the Gaussian distribution that you might be used to looking at, or the bell curve or the normal distribution. And so what we see is instead of a Gaussian distribution, we see a tail of events, which is what we would call a power law or fat or heavy tail. And what it is instead of a Gaussian distribution, this sort of a distribution, statistical distributions, means that you're more likely to have big events occur than you would with a Gaussian distribution. If you're interested, if you have particularly mathematical students, and you're interested in bringing this into your classes, please write me, and I'll explain how you might bring this in to your classes. Triggering events in road networks. So this is research I've been doing with my PhD student, Faith Taylor, who is at the EGU here. There's another actual abstract that I'm supposed to be doing that I'm co-author on right now, and she's speaking over there, or she would have come to this. And the idea here is I'm now interested in taking somewhat theoretical ideas and saying, what can we do in the real world with some of these ideas? So this is a road network. I picked Salta province because I lived up here for 3 months. It's a beautiful area of the world in Salta. And you have many different kinds of roads here, principal roads and primary unpaved roads. And what I was curious about is, well, can we do something about probabilistically looking at how landslides intersect with road networks? And the reason we're interested is because landslides cause a lot of damage to road networks. So here we have an example of a landslide, another one. This one here caused this route to be shut for months. So they're very, very drastic. And the idea is if we know the probability ahead of time, then maybe we can do something about that. Maybe we can plan ahead of time. We can mitigate. So we take the road network here, we take the statistical distribution I just showed you, and I'm going to randomly pull landslides from this. And it's like a game. It could be like throwing a coin and saying, where does it land? Am I going to have a big landslide or a medium landslide or a little landslide? And I'm going to be more likely to have a landslide around this side than I am going to have a landslide of this size. And what we do is initially we put this into, here's a road, here are my landslides that I drop, and here are the roadblocks. And we do this thousands of times. We vary the road network, we vary the landslide density, we use an open source program to do this in, and we add reality so that we count the number of times the roadblock. And I'm going to show you a bit more a more in-depth example of this in a moment. So I'm going to show you now an example from Colezzone, Italy. Excuse my pronunciation in Italian. These will simulate the landslides. We'll take a road network from the area with the simulated landslides and the resulting road blockage, and then we'll look at just the resulting road blockages. And this is all being done in a computational model. In the computer, where we have a grid, we have the road network, we randomly drop landslides on the road network, and we count how many times they drop. So here's our road network, 20 kilometers here for scale. Here are the landslides that we've randomly dropped on here. These are not real landslides. These are random ones that we've drawn from our probability distribution. And then we count the road blocks here. And so these are some examples. And we find over this 400-kilometer region, there's 1,360 kilometers, 400 landslides are dropped. And on average, one landslide has blocked the road for every 12.5 kilometers of roads. This is something we can then hand civil protection agencies, and we can say, well, if you have an event of this side, on average, this is how many times the roads will be blocked, and on average, how often. So let me show you a video of this in action. Thanks to Faith for doing this. So this is a model. This is the 400-kilometer region. And here we have the road network, and we're randomly dropping the landslides. So they're being randomly drawn from the computer model over time, all part of one triggered event. And then we see, okay, they've actually blocked the roads, and we find the one block every 12.5 kilometers. Okay, let us move from there to hazard assessment of mass wasting. So can we do hazard assessment? Can we use some of the tools, the past history of landslides, the ideas of gravity, the ideas of water, to do hazard assessment? Yes, we can. And this is where I started the talk saying we can tell where will be higher susceptibility and lower susceptibility for most parts of the world. In most cases, areas prone to such hazards can be recognized with some geologic knowledge. Slopes can be stabilized or avoided. And this gets into our first question, who's going to pay for it? That's always the issue. Warning systems can be put in place that minimize the hazard for places that we can't put money in. So here's an example. Here's past history of landslides. Here's a slope map. That's for gravity. Here's the geologic mapping. This results in a landslide hazard map where red is high hazard, yellow is medium hazard, and green is low hazard. Something fairly simplistic. The question is, will it be used? And in some countries it will be used, in other countries it won't be used. Now, there are many case histories of mass wasting disasters in the past. I've mentioned this a few times. Looking at the events in hindsight shows us that hazardous conditions and previous history existed prior to the event. So we knew that there could be an issue. So we can make maps. This is a landslide overview map of the conterminous USA. Great, we have high hazard and medium hazard and low hazard indicated here. But is it useful? Well, this is not very, very local. So if we want to get more local, then we have to do higher resolution maps. That means we need more information. We need more human power. We need more resources. And we need the people trained to do it. Why don't we do this everywhere in the world? We don't have the resources to do it right now. This is an example for Camarines Sur. This is high susceptibility, moderate, low susceptibility, absent, and so they created it. And then you come to another issue is there's huge areas here which are being indicated as high susceptibility. So what do the civil protection agencies do if they're given a map that says everything here is high susceptibility? Well, they can't prevent people from living there, and they can't do the resources, so all they can do is say you're living in a high susceptible area. So planners can use these maps to make decisions about land use policies. They can take steps, but some of the barriers that exist are resources of money, resources of time, and just the ability to protect ourselves. Let's move to the last major section, prevention and mitigation of mass wasting. This was in China when I was there 3 months ago. This is an example of a check dam in an area which actually had the severe fatalities that I'm telling you about. And this is basically that if a debris flow comes down off the mountain, it is to protect it, but it allows water to get through. It is humongous. This is one of my other PhD students there. We spent 10 days touring about 1,500 kilometers of northwest China in the Gansu area. Slope assessment. All slopes are susceptible to mass wasting. We know that. If a triggering event occurs, thus all slopes should be assessed for potential mass wasting. Mass wasting events can sometimes be avoided by employing engineering techniques, like what we just saw and what I'm going to show you. Examples include shotcrete, concrete, metal mesh, retaining walls. This is an example of shotcrete being sprayed onto the side of clearly a slope, which is not at the angle of repose. The angle of repose would be more like 37 degrees. Here's another example at the Wadi Adai. Here is a retaining wall before and afterwards. This was an advertisement by this engineering company for how nice they make it. I would actually question a little bit this. Actually, I won't do that on video. Okay. This is an example in Taiwan. And here we can see examples where they have tried to create concrete barriers. You can also see these drainage channels here, and the drainage channels become very important to take some of the water away so the hill slope does not become so heavy. Here's an example of a debris chute in the Alps. Then you have things like rockfall sheds. This is in Taiwan, and literally roads or highways go underneath them, and they just allow the rocks to bounce down and come back down, but then someone's going to have to clear all those rocks afterwards when it gets too heavy. Drainage pipes become very important. They are inserted in the slope to more easily allow the water to get out, and you'll see these in many places. The problem is the upkeep of them. What happens when, in addition to water here, maybe the mesh fails and you start to fill with sediment? Someone has to go in and clear these out. So there are issues there. Now, there are other engineering techniques. You can take over-steepened slopes and you can regrade them. So instead of having a road barrier like this next to the road, you then make it and you fill in sediment so that you create it so it's at its angle of repose. What are other examples of mitigation techniques? In mountain valleys subject to mud flows, plans can be made to rapidly lower the level of water in human reservoirs. So now we get into what humans can do ahead of time. Warning systems can be put in. Land use planning can be put in. Warning signs. This is an example of a photo I took when I was in Taiwan. I recognize the characters for xiaoxin, which means careful, and my Chinese isn't good enough for the rest of that. And then we have the Isle of Wight here, which is off the UK, and you see very similar things to warning people. We can also monitor when we know that slope is in movement. So these are examples of different boreholes and tensiometers, literally putting a spring into the earth. And the spring will expand as the earth starts to expand. So we expand, that's hooked up to some electronics, a log, which we then know that something is occurring as part of that slope. Good, so I'm well within 40 minutes right now, and I want to talk a little bit about further resources. So thanks to my PhD student, we spent a couple of hours and we went through to try and come up with some resources in addition to what I've already shown you here, which you can use with your students. These are all general landslide information. Each one has the citation, what it is, the web address, and then a little blurb on why it might be of interest to you. You will have access to these slides, is my understanding, after this is over. I will make sure that this is easily readable in the PDF that you will get. These are landslide videos and photos, because really landslides become a bit more relevant when students can see the photos, but in particular the videos. The particular one I want to point you to is David Petley's blog here, and he has the ultimate compilation of the best landslide videos. This was as of 2012. And some of them I've shown you here, but there are 15 or 20. These are all public domain, so you can use them freely. The next one are web, activities and teaching resource. Some of these are more aimed at elementary school, some of them are junior high, some of them are high school, but they're different activities like the one I showed you just now in taking a bottle and rotating it. So there's a whole bunch of different activities that you can use here with your students. Some of them are half-day activities if you want them to be. Okay, I'm going to move here to questions, and in the background while we're doing questions is a video that I took on the 13th of September when I was on my trip in China. Carlo was doing an outreach meeting in Italy, I was in China, and we happened by a landslide. So I'll show a video of that and take any questions or comments now. Let's turn the sound off. Good. Okay, so any questions or comments or concerns? Yeah.
I'm a bit confused with terminology. So many terms mentioned. First of all, mass wasting. Is that a synonym of landslides?
Yeah, so the question is terminology, and mass wasting is a synonym for landslides. Now, we often differentiate landslides and rockfalls in the technical literature, and we call everything mass wasting that involves gravity or water that is flowing downhill. So landslides are formally a part of mass wasting, but in general we just say landslides for everything, commonly.
Maybe that is a linguistic problem. Wasting mass becomes a period.
Yeah. The derivation of the term is mass as in sediment. So if I take sand or gravel or vegetation, any regolith, that's my mass. And the idea of the wasting is that it is moving from one place to another, and that's where the term was kind of derived from. Yeah, so I agree. So I've just put it up there so that people can see that that's what they'll find in the literature sometimes. Yeah, so a lot of these terms, and if you would like, I do classes on natural hazards for first-year students, and I do 4 hours on mass wasting. If people would like, I can send to you individually, because of issues about copyright putting them online, because some of the stuff are from other people. I'm happy to send you the lecture notes from that, and there I go into detail, debris flow and rock falls and all of these with many pictures and videos. So please email me and I'll send it to you by private email. Okay? Yeah. Okay. Yeah. Yeah, so the question is about modeling of landslides in the classroom. Sadly, because my classes now are numbering 90 or 100 as opposed to when I was a high school teacher and had 10 to 30, I haven't been able to do as much hands-on experiments in the lab. A lot of the resources that I've given on the third slide are actual experiments one can do. Now, I did originally try to do some modeling where I would take sand, and it's very important that the sand is not homogeneous. So what that means is it can't all be the same size and type of sand. You need heterogeneous sand mixed with different things, and then you can do things, you can observe better the sand particles. So one thing you can do is you can literally drop grains, and you can use a funnel to do this very slowly, and form a sand pile. With the sand pile, you will see landslides starting to form. And some of them will be small, some of them will be big. Then you can add a tiny bit of moisture to that. And so this is an example of an experiment. I've done this on my own and not with the students, just due to time. And you can only do this with 9 or 10 students, really. Okay, so there are a number of things one can do. They're quite fun. The one with the bottle here that I showed you is very inexpensive. I'm just going to grab it. So this is very easy to take. You just take some sand, you rotate the bottle very slowly, and you tell the students to observe the different size landslides that are coming as a result. Then you add a tiny little bit of water, and you do it that way. Don't do what I did, which is take a huge bunch of sand, a big piece of cardboard, some water, and it wasn't working. I kept putting more and more water into it, and finally it collapsed as a landslide and spread over everyone in the first row. So now I use a bottle when I'm doing these sorts of demonstrations. Okay.
Bruce, it's hard to imagine to get a more concise and condensed and excellent overview on the different aspects of landslides and so many resources. Thank you so much. This is very helpful for us. Thanks very much.